Friends, we would like to find out the liquefaction potential of a site using cone penetration test data. So today, determination of liquefaction potential of a site using cone penetration test. We call it CPT. And we will be using the simplified procedure. The simplified procedure is given in IS 1893 part 1 2016. So what we know is the tip resistance of a cone. So knowing the tip resistance, what we measure it. So at a site, when we go to the site, we perform cone penetration test and we measure the cone tip resistance, which we call it QC. So this is known to you. And we also measure the sleeve friction. And then once you measure at the site the value of QC, this QC needs to be normalized. So you will have to go for normalization or normalized dimensionless cone penetration resistance, which we call it QC normalized. So QC1, from QC it is going to be QC1 normalized, and this is given in the code. This is equal to correction factor CQ into the measured value of the cone tip resistance QC divided by atmospheric pressure, where CQ is correction for overburden pressure. So very simple way you can find it out. This CQ, which is called the correction for overburden pressure, is going to be equal to atmospheric pressure, PA, divided by effective overburden pressure raised to power n. This value of n, so CQ is given by this expression, and the value of n is going to be 0.5 for sandy bed. So at the ground, at the site, if it is sandy soil, then the value of n for calculating CQ will be 0.5, n equal to 1 if it is clay soil bed. So the value of n is known to you. Now, once you calculate the value of CQ, QC is known to you. Atmospheric pressure, PA, is the atmospheric pressure, which is equal to so much of kilopascal. So this is known to you. This you have measured. CQ you have calculated because you know the atmospheric pressure and you can calculate the effective overburden pressure at the given depth. So at any depth, we can calculate the effective overburden pressure. And depending upon the ground condition, whether it is sandy or clay soil, we can take the appropriate value of n. And therefore, from expression 1, we are in a position to get the normalized value of cone penetration resistance. So this is the normalized value, n for normalized, and this is the corrected value for QC. So QC has been normalized, and having got this, this is to be again corrected for clean, equivalent clean sand. So QC 1N, which is the corrected value for overburden, is corrected again for an equivalent clean sand. Clean sand. If at the site you find that it is clean sand, then no correction is required. Then in that case, the QC1N for clean sand will be equal to QC1N. But if it is going to be, say, having fines more than 5%, or it is going to be silty sand, so depending upon the percentage fines, you need to correct it, and it is corrected to an equivalent value of clean sand. Therefore, we can say QC1N for clean sand, CS means clean sand, is given by a factor, a correction factor Kc multiplied by QC1N. So Kc is called correction factor for grain characteristics. Characteristics. When a sand is called a clean sand, when the percentage fines are going to be less than 5%. Up to 5% it is going to be clean sand. So you need to find out the value of Kc. So in order to find out the value of Kc, The expressions given in IS 1893 should be used. This Kc value is given equal to 1 for a non-dimensional quantity IC less than equal to 1.64. We will see what IC is, how to calculate this. This is equal to minus 0.403 into IC4 plus 5.58 IC cube minus 21.63 IC whole square plus 33.75 IC minus 17.88. This expression is for IC greater than 1.64. So how to find out this dimensionless quantity IC? This IC can be calculated very easily by using one expression which is given in the code. This is equal to under root 3.47 minus log q whole square plus 1.22 minus log of f whole square. Where q, what is this q? That is also a dimensionless quantity. This value of q can be calculated very easily by knowing the value of cone tip resistance QC minus what is the vertical overburden pressure, total vertical overburden pressure divided by atmospheric pressure multiplied by the atmospheric pressure divided by effective overburden pressure raised to power n. So that is the value of Q. And therefore, Q can be easily calculated. So Q is going to be, in fact, if you look to this, is going to be CQ multiplied by this quantity. And this is also a dimensionless quantity. Now, how to find out this value of F? The value of F can be easily calculated in percent. So 100 into slip friction. I've already told you that slip friction in CPT is termed as Fs or designated as this divided by the measured value of cone tip resistance minus the total vertical overburden pressure. So this is the Fs is the measured slip friction. QC is the measured cone tip resistance, and this is the calculated overburden pressure at any depth that you can always calculate it. Now, having got this value of Q, got the value of F, substitute in this expression IC, and you can get the value of IC. Depending upon the value of IC, if it is less than equal to 1.64, then take the value of Kc equal to 1. So for clean sand, you get the value of Kc. But if IC is greater than 1.64, you have a long expression, and that needs to be used to calculate the value of Kc. Once you know the value of Kc, then for clean sand, it is Kc into the normalized value of QC1N. So this way you can calculate as per the codal provision. So now I know the value of QC, normalized value for clean sand, and once you get it, if you see the IS 1893 in figure 9, it is given that QC1N normalized value for clean sand, which is equal to Kc into QC1N. And here on the y-axis, it is given in the chart that value of cyclic resistance, CRR we call it. CRR for 7.5 magnitude of the earthquake, and this is something like this. So from this, you have the values on the x-axis for clean sand, and for corresponding value of QC on the y-axis, you can find out CRR for 7.5 magnitude of the earthquake. So this is for MW, magnitude of the earthquake is going to be 7.5, and this is for clean sand. Clean sand means percentage fines are going to be less than equal to 5%. Now therefore, cyclic resistance ratio for any magnitude will be cyclic resistance ratio for 7.5 magnitude of earthquake multiplied by the scale factor, which is called MSF. In the last example, we have solved it, multiplied by K sigma, which is for correction for overburden, if the depth is more than 15 meter, multiplied by K alpha, where K alpha is the for horizontal ground. If the ground is horizontal, level ground, then K alpha is going to be unity. So this expression will give you the value of CRR. So this is the final expression. So this is the easier or simplified way of calculating the cyclic resistance ratio. Having got this cyclic resistance ratio, you can calculate the value of cyclic stress ratio for the given magnitude of the earthquake, which is given as 0.65 into maximum or peak ground acceleration divided by acceleration due to gravity multiplied by at a particular depth what is the total vertical overburden pressure divided by effective vertical overburden pressure into reduction factor. The formula for reduction factor is already given in the last videos, and how to calculate this A max by G. It's a function of the zone factor, in which zone. So this will be given to you, A max upon G, and therefore you can calculate this value of CSR. Having got this, therefore, the liquefaction potential of any site, you can find it out by calculating the factor of safety, which is equal to the cyclic resistance ratio, CRR, which you obtain from this, divided by CSR. And if it is greater than 1.2, there will not be any liquefaction. That means the ground will not liquefy. But if it is less than that, then the ground is susceptible to liquefaction. So friends, today this theory we have done it as per the codal provision, and in the next video we are going to solve problems over this. So one by one we will be dealing with different types of problems for calculating the liquefaction potential of a site. Thank you very much.